So this is section 13.5. This is actually a pretty quick section. This is on directional derivatives. And so it poses a very simple question. So think about the two partial derivatives we've looked at so far. So for example, given f of x comma y, we know two things. We know that f sub x of xy, this is the partial derivative, let's say partial with respect to x. What this means is, as we go in the x direction, now we can also think of the x direction as the I direction for a vector. How does f change? And likewise, f sub y, we can think of this as we go in the y direction, but the y direction can be thought of as the j direction. How does f change? The kicker is we might be interested in what goes on if we go in yet a different direction, like not just I and j. So how about, let's say, if we went in the direction of, say, a vector A, which is 2i plus 3j, right? How does f change? So we're not moving in the x direction, we're not going in the y direction, we're going sort of in a combination direction. So this leads us to the definition of the directional derivative. So here's the definition. So I'll give this with 3 dimensions, but the 2-dimensional version is just as easy. So given a function, say f of x, y, z, and a unit vector. So we need a unit vector to give a sense of direction. So the unit vector will be u, which will be ai plus bj plus ck. So the a, b, and c are the coefficients. The directional derivative of f in the direction of u this is a very long definition, or very long term. This is denoted capital D sub u of f of x, y, z, and equals so let me write down the term for it, d sub u f of x, y, z. So what we do is we take a, the I component from the vector, we multiply it by f sub x, b times f sub y, this looks a bit like a dot product, which is great, plus c times f sub z. Now, to be fair, this is a definition that I'm giving. The actual definition is a limit definition, which I'm not going to give. So really this definition is sort of an alternate definition. This is just to keep in mind, there's sort of a hiding technical definition. And so what this tells us is exactly what the question asks. So in 2 dimensions, there's no c. It's simply a f sub x plus b f sub y. So what I'll do is I'll clear the screen and I'll do an example and I'll make a final note, and that'll be it. It's actually a very short section. So for example, and I'll give an example that we can understand in real world terms. So we'll get back to this example of a function giving us a temperature. Say something like x squared y plus, say, y cubed. Suppose this gives the temperature at x, y in degrees Celsius with x and y in meters. So suppose I need a unit vector to measure this. Suppose that u is the unit vector in the direction of 2i plus 3j. We'll find and we'll interpret d sub u f of, say, 3, 5. All right, so first of all, for a solution, we need to look at this point that it made about u is the unit vector in the direction of this. So what we need to do is we need to make this a unit vector. Right? So we make a vector a unit vector by dividing by its magnitude. So we'll take ui plus 3j, make that a unit vector in order to use the definition. So we take 2i plus 3j divided by its magnitude, square root of the sum of the squares, we get a nice unit vector. So then we need f sub x and f sub y. So f sub x is 2xy, f sub y is x squared plus 3y squared. This tells us the directional derivative at a point. Now, notice I'm not actually going to fill in the u in this notation right here. I'm just going to write d sub u of f of xy, and that's it, because otherwise it'd be icky. You could fill in the vector, but nobody ever really does. So what I do is I take the a, which is 2 over root 13, times the f sub x, plus the b, 3 over root 13, times the f sub y, and that's our result. Then we plug in our point of interest. So we get 2 over root 13, and this is at, let's be clear here, let's clear that out. This is at the point 3, 5. So plug in 3 for x, 5 for y. So this simplifies a bit. So the numerator, I get 4 times 15 is 60 over root 13. For the second one, we get 5 squared is 25 times 3 is 75. Plus 9 is 84 times 3 is 252. So what we get at the end, we get 312 over the square root of 13. So this is approximately, I'm going to fill in approximately just because it'll help give us an idea. It's approximately 89.6. So what this means is, if we're at the point 35, heading in the direction of u, the temperature is increasing. This is an instantaneous increase, like a slope. At 312 over root 13, or approximately 89.6 degrees Celsius per meter. So as a slope, it's a degrees per meter because it's divided by distance. So very simple example. So all I want to do now is close with 2 notes. So note A is that don't forget to make the vector unit vector. And note B, otherwise you'll get the wrong result. And note B is we can think of this as a dot product if we like. All right, notice that and this will come up in the next section, but it's a good thing to mention it here. This is A f sub x plus B f sub y plus C f sub z. You can rewrite this if you like as the dot product between this vector, which is u, and a vector composed of these three. Now, this won't be so relevant right now. It'll be relevant in the next section, which we'll hit shortly. But I mention it now just to sort of refresh your brain on the dot product. So I could write it this way. There's no real point right now, but interesting fact nonetheless. So that is it, a quick section. That's the end.